Okay, the next thing I want to talk about is applications of flow control. When is flow control important? One example is if you're going to do point of use treatment. So if you're going to treat water in your own home, then you need to figure out some way to control the flow rate through your little treatment device. Otherwise, it's not going to work as well. Examples are clay pot filters, slow sand filters. Maybe you're trying to remove arsenic and fluoride. And I really should have had some images here, but apparently I was too lazy. When I was in Honduras in the 80s, I was trying desperately to make a slow sand filtration device that would work for my own home. And one of the critical pieces is figuring out how do you get flow control to work nicely. We need to add chemicals for a water treatment plant. So some aluminum or polyaluminum chloride as a coagulant. And we need to control the dose of those and make it easy for an operator to increase or decrease the dose. So that ends up being critical. Another one is chlorine for disinfection. Maybe you need to add sodium carbonate or hydrochloric acid, sodium carbonate to control pH, hydrochloric acid to drop the pH a little bit to prevent calcium carbonate precipitation. One of the things that we've done in one of the plants in Honduras, and yes, you need to worry about whether you end up dropping the pH too much and you're causing solubility of lead in the distribution system. So if you have electricity, then this is what you do. So you use a metering pump. So here's a piston pump. Piston pumps are great and can be used to meter chemicals. The problem would be that the piston itself, that whole system needs to be compatible with the chemicals that you're using. And so this would not be the way you would want to meter chlorine. You can use a gear pump. Gear pumps are fascinating. Yeah, also lots of sliding surfaces and another issue of making sure that everything is chemical compatible. There's peristaltic pumps. This is the system that you would have in the Agua Clara lab that you're building there at OSU. Peristaltic pumps, the easy way to think about it is if there was a garden hose laying out on the ground and you walked down the garden hose, putting one foot in front of the other, and as you're going, you're squishing the hose, you would push some water out the end of the hose. That's all a peristaltic pump does. And the cool thing about a peristaltic pump is that the only thing that touches the fluid is the hose. So the rollers that are smashing the tubing don't ever touch the chemicals that are inside the tubing. And so you can pump really nasty chemicals with a peristaltic pump. Same thing with a diaphragm pump. In some ways, it's very similar idea. You have some flexible membrane that you're pushing back and forth, and that's acting like a piston, but it's flexible and there are no sliding surfaces, but there's a surface that has to deform. So some cool ideas. Another completely different idea would be that you would have maybe a stupid pump, like a centrifugal pump or maybe a gravity powered system that's providing pressure and pushing water towards your water treatment plant. And you could control the flow of that water by having a flow sensor that's measuring head loss and using that to figure out what the flow rate is perhaps. And then you could have a computer that controls how far open the valve is to control the flow into the plant. That is a very, very common system used in water treatment plants for controlling main flows, main flow into the plant or controlling flow into the filters. And what I am learning about that system is that very, very frequently, those systems have problems with cycling, where they have lousy control on the software side. And so it ends up cycling and you end up not getting the nice consistent flow of water through your plant that you would like. But it's an option. And so my conclusion here is one option is to just raise the per capita income of everybody on the planet, make everybody have access to electricity and easy access to all these parts. And then all this stuff works great. And indeed, that's true. Like if you're in a community here in the US, they can afford to replace their their pumps every few years, and that whole system works. And I would argue that there's another approach. And the other approach is like going down a completely different path of this evolutionary chain that we're on, where we, instead of using pumps, we figure out a system that doesn't have any moving parts, but that still uses good physics to make it work well. I already talked about those observations. Well, I'm going to talk. Yeah, and another example of dosing, and I think I'm showing these because when we began this journey of wanting to design water treatment plants, I recognized that figuring out this part of how do you dose the chemicals was like top priority, because if you don't have that working, none of the rest of the plant works. And so that became the very first task that we worked on starting in like 2004. We started hitting this question about how can you make a good system for dosing chemicals? And what's fascinating is, like, that was in 2004. Like, people have been doing water treatment for a very long time, and yet there weren't great examples of how you dose chemicals if you don't have access to electricity and to pumps. And here's another example. Here's a saltwater electrolytic chlorine, which I misspelled, generator. And so there it is. It was in a town in Nicaragua, in Concordia. And what's fascinating is I realized when I looked at this that it wasn't working. And I walked around to the back of it and I saw this. So on the back side of this was another chlorine feed system. That T is, the cap of that T is meant to be removable, although I tried and couldn't. And what you do is you drop a chlorine tablet. So like, it's like a hockey puck of chlorine that you would drop in that T, and you might drop several of them in there. And then some of the water is flowing past that T and dissolving that chlorine tablet over time. And if you get the flow rates right, because you don't send all the flow past the hockey puck, you only send some of the flow that's going into your storage tank past the hockey puck, you can kind of regulate the dose. I'm still waiting to see, someone must have done studies on these to figure out how good they are. This is an option. You can buy this in the US. They're being installed many places on the planet. I've always been skeptical about how good the chlorine dose is as a function of time, but maybe it's not bad because they're being used many places. But what's interesting here is I'm pretty sure that that system wasn't being used either. So there was like Plan A, not in use, the one that required electricity. Plan B, also, as far as I could tell, they weren't adding any chlorine. And this is a place where an Agua Clara plant went in as Plan C, I guess that would be, or Roman numeral 3. Okay, so we're going to talk about different ways to control flow, and we're going to start with this hole in a bucket idea. And this comes from Honduras, where they have chlorinators on storage tanks. So we're out in the mountains, and there's this distribution tank. You can see the pipe from the mountain spring or stream comes here, and it goes up and dumps into the top of the tank. And then there's this mystery little cube on top of the tank. And that mystery little cube is a place where there's some magic happening. So this is what's inside that magic tube, inside that magic cube. So there's the magic cube. It's a little tank where you would mix up a chlorine solution using calcium hypochlorite. And then there's a PVC pipe coming out the bottom, and there's a valve at the end here. And you can open or close that valve to set how fast the chlorine drips out of that tank and added to the raw water that's coming into the tank from the stream. Any questions about how that system is working? You got a tank of chlorine that's on top of the of the tank that's going to be your storage tank for water. Water's coming into your storage tank, running by gravity day and night, and you're dripping chlorine in from this little storage tank. So what happens to the chlorine flow rate over time? So what happens over time? The chlorine level drops in that tank. And so the elevation difference that's pushing the chlorine through that valve is dropping. And you can think about that orifice equation again, where the flow rate goes with the square root of the height. Or said another way, the head loss through that valve is proportional to V squared. In either case, you see that as the height goes to zero, the flow goes to zero. And so as the chlorine solution is used, the dose of chlorine changes. And that's not at all what we wanted. We wanted a system that would give a constant chlorine dose all the time. And so this isn't working. But what's interesting is that, well, I'll come back to that in a second. This is why it doesn't work, because of the orifice equation that says that the flow is proportional to that delta H. So we're going to find out what does the flow actually do as a function of time? And the derivation for this is in the textbook. The derivation involves integration. It's not that complicated, but the result is what's really cool, and it's what I'll show here. This is a result of taking into account the orifice equation, or another head loss, like minor loss coefficient equation, and tracking volume in the tank as a function of time, and comparing or having an equation that relates the height of the chemical in the tank and the volume of chlorine in the tank. So this is the beautiful equation that we get, that the flow rate at any time divided by Q0, the initial flow rate, is equal to 1. And if we stopped right there, we'd be really happy, right? If Q over Q0 would equal 1, that would mean that the flow rate at Q is Q at any time. That would mean that the flow at any time is the same as, is equal to Q0. But there's this second term in the equation, 1/2 times T over T design times H tank over H0. And that's what's going to get us, because as T gets larger and larger, that second term gets bigger and bigger, and my Q decreases, gets smaller and smaller. And so what's getting us? Well, as T increases, T over T design is the time it would take to drain the tank if the flow was held constant. So you filled up this tank, you set an initial flow rate, and you said, okay, at that flow rate, this is going to last 4 days. So that's T design. And when you come along and you come back at T equals 4 days, and if H tank was equal to H0, you would find out that the flow was exactly half of what you had expected it to be. So some reflections on this. If we let the discharge to atmosphere be located at the elevation of the bottom of the tank, so if H0 is equal to H tank, then the flow rate goes to 0 exactly when T equals 2 times T design. So you can look at that. When T equals 2 T design, then this second term is equal to 1. And that means that Q goes to 0. So that's how long it takes for the tank to drain. It takes twice as long as what you had initially expected based on the initial flow rate. So this is a nice result. What's the average flow rate during this process if the tank is drained completely? So if it takes twice as long to drain as what you would have initially guessed, it's because the flow rate on average is half of what you had expected. So the average flow rate out of the system is half of the initial flow rate. So if you take a tank like your bathtub and you fill it up and then you drain it, if you would measure the initial flow rate out of the bathtub when the bathtub is full, And if you would use that to predict how long it would take for your bathtub to empty, you would come up with a time that is exactly 1/2 the time that it's going to actually take to empty the bathtub. Okay? Kind of a cool, simple result. The average flow rate is 1/2 of the initial. But now the question is, we're trying to get this to work and to be much better. How could you modify the design to make it so that the Q is more constant? So take a look at that equation, or maybe your intuition will kick in. What could you do to change something so that the flow rate Q is always equal to Q0, or close to being equal to Q0?